everyone, welcome to the first lecture of Chapter 4. Today we are going to talk about stoichiometry and also limiting reagents and percent yield. So for stoichiometry, we are always going to be converting from the mass or volume or number of moles of one thing, right, maybe of a reactant, and then we're going to calculate the mass, volume, or moles of maybe a product. Right? But we're always going to change compounds in between. So that is what stoichiometry is. So the first step will always be to balance the chemical equation. You'll either be given the chemical equation or you'll be given a word problem, in which case you will need to write the chemical equation. But then you always need to make sure that the equation is balanced. If you see that you're using a 1-to-1 ratio, make sure that you've gone through and checked that it really is a 1-to-1 ratio and you didn't just forget to balance the equation. Your second step is if you have, if you're starting with grams or you're starting with maybe liters or milliliters, you'll convert that into moles, and then you can use the mole ratio from that balanced chemical equation to change into whatever you're trying to find, right? Whatever substance you're trying to find. Maybe you're trying to find your product or your other reactant, but you use the mole ratio to change compounds. And then your last step will be to convert your moles of that compound into grams or volume or whatever you're trying to find. So this is kind of a roadmap. If you are not strong at stoichiometry, you might want to use this to help you. I've put this into the Chapter 4 module on Canvas, and it just tells you how to get from one thing to another. Like if you're starting with mass and you need to get to moles, you're going to use 1 mole equals molar mass to get from mass to moles. And then, to get from moles of one thing to moles of the other thing, you're going to use the coefficients from the balanced chemical equation, which I will often call the mole ratio. And then, if you wanted to get from moles of one thing back to mass, then you would use 1 mole equals the molar mass again. And so you've got, if you were using particles like atoms or molecules, it tells you how to use that, or volume for gases at STP, you'll use that 22.4 liters. But this is mostly what we're dealing with right now. So let's go ahead and do an example problem. If we have 6.50 grams of aluminum reacting with an excess of oxygen, how many grams of aluminum oxide are formed? So we would write our balanced chemical reaction. We have aluminum reacting with oxygen, and remember when oxygen is by itself, it always needs to have a 2 after it because it is a diatomic molecule. And we know that it is a diatomic molecule because it is a member of Hofbrinkel. Aluminum does not need a 2 after it because it's not a member of Hofbrinkel, it's not a diatomic element. And then it says, this is going to be a combination reaction. We have aluminum reacting with O2 to form aluminum oxide. And so to figure out the formula for aluminum oxide, remember aluminum is a 3+, oxygen's a 2-. We can circle and switch. So we know the 2 goes with the aluminum and the 3 goes with the oxygen. So we get Al2O3, and then we can go through and balance our chemical equation. After we've balanced our equation, now we can start to set up our stoichiometry problem. So we're starting with grams of aluminum, and we are needing to figure out how many grams of aluminum oxide are formed. So this is a grams to grams problem. We're going from grams of one thing to grams of another thing. And it says that there's an excess of oxygen, which just means that we don't need to factor our oxygen into our calculations in any way. We're going to learn how to deal with when we have 2 different amounts of reactants later in this lecture. So let's go ahead and get rid of that. We're trying to find grams of aluminum oxide, and we are starting with grams of aluminum. And so grams of aluminum will go in the beginning of our train track. Now remember, we are always going to cancel units down and to the right. So if we have grams of aluminum that we're starting with, we need to have grams of aluminum down on the bottom. So we will use the molar mass of aluminum from the periodic table to convert grams of aluminum into moles of aluminum. Make sure that we're always checking that our units are canceling. And so now we're left with moles of aluminum. Once you get to moles, now you can use the mole ratio to change from moles of one thing to moles of another. And the way that we're going to do that is we're going to use these coefficients from our balanced chemical equation. So we're needing to cancel moles of aluminum down and to the right, and we're going to use that 4 from the chemical reaction. We have 4 moles of aluminum in our chemical reaction, and when 4 moles of aluminum react, it's going to form 2 moles of aluminum oxide. So that will go on the top. So here, these numbers are from the balanced chemical equation. That is our mole ratio. For every 4 moles of aluminum that react, 2 moles of aluminum oxide are formed. This is the only time that you're going to use a number other than 1 in front of the word mole. Whenever we use molar mass, it's always going to be 1 mole, but here, this mole ratio is always going to be the numbers from the balanced chemical equation. So then our moles of aluminum cancel out, and we're left with moles of aluminum oxide. And then we can go ahead and use the molar mass of aluminum oxide to figure out how many grams there are. So our moles of aluminum oxide cancel with moles of aluminum oxide. We are left with grams of aluminum oxide, which is what we are trying to find. And then we are going to punch all of that in our calculator. Remember to multiply all of the numbers on the top and divide by all the numbers on the bottom. So we have 6.50 times 2 times 101.96 divided by 26.98, and this is important, divided by 4. Okay, make sure for every number that's on the bottom, you're hitting divided. If you hit divided by 26.98 times 4, because you're like 26.98 and 4 are both on the bottom, that will make your calculator think that this 4 is up on the top, which is not what we want. So we want to hit divided by 26.98 divided by 4 to avoid any calculation errors, and then you'll get your answer. Make sure you're always rounding for significant figures. Since this is all the multiplication and division rule, we look for our lowest total number of significant figures. The mole ratios are going to be considered exact, as well as the ones that go with the molar mass. Those are all exact. So we have 3 here, 5 here, and 4 here. So our answer is going to have 3 significant figures. So sometimes when you are doing a stoichiometry problem, you will be given amounts of 2 different reactants. So you'll be given amounts of, say, in the last problem, you would have been given an amount of aluminum and an amount of oxygen. And one of them will always be limiting. It will be there will be less of it. And usually it's the one, like in practical experience, it's usually the one that's more expensive because you don't want to waste a really expensive reagent. But whichever one you have less of is called the limiting reactant or the limiting reagent, and it's the one that gets used up completely in the reaction. The other one will be called in excess. So we have one that's limiting and one that's in excess. And when we're trying to calculate how much of our product can be formed, we're always going to use the one that's limiting, right? Because the other one will create extra, which we won't actually be able to make because we're going to run out before then. So when we're asking about the theoretical yield will always be the amount of product that you can make from that limiting reagent. And it's called theoretical because this would be if your reaction went perfectly. If you got 100% yield, if nothing went wrong, nothing spilled, no gas escaped at all throughout the entire reaction, which will never ever happen. So that's why it's called a theoretical yield. In theory, if all went well, that's how much we could make. So here's my example of just kind of an everyday limiting reagent. If you had 8 slices of bread and a jar of peanut butter, how many peanut butter sandwiches could you make? And we're going to assume this is a really big jar of peanut butter. You're not going to run out of it, right? You could make 4 sandwiches because you have 8 pieces of bread. For every 2 pieces of bread, you make 1 sandwich. And so you can only make 4 sandwiches because then you would run out of bread. But you'd have peanut butter left. So the bread here is our limiting reagent, right? Our limiting item, and our peanut butter is in excess. So let's figure out how to do this using chemistry. If we have 4 moles of hydrogen mixed with 2 moles of chlorine, how many moles of hydrochloric acid can we form? So the first step is to always write a chemical reaction. So here we go, we have H2 mixed with Cl2 gives us 2HCl. And so we check, we make sure it's balanced, all that good stuff. And the way that we're going to do this is we're going to make 2 separate train tracks. So if you'll look, hydrogen, right, we're starting with an amount of hydrogen and an amount of chlorine. Both of those are reactants. And it's asking how much product can form. So that's how you're going to notice that this is a limiting reagent problem. When you're given both reactants and you're asked to find out about the product from both of them, that's a limiting reagent. So the way that we're going to approach this is we are going to make two different train tracks. One of them is going to start with your moles of hydrogen, and the other one is going to start with your moles of chlorine. Both of them we're trying to figure out how many moles of hydrochloric acid. So let's deal with our hydrogen first, right? We're going to, here we go. Two separate calculations, two sets of train tracks. The limiting reagent will be the one that produces the smaller amount of product. So here we are. If we were to calculate our moles of hydrogen chloride from H2, so we put our amount of hydrogen in the beginning, and we make a train track, and we're going to use our mole ratio to figure out how many moles of HCl can form. So for every, right, we don't have a coefficient here, so for every 1 mole of H2, we will make 2 moles of HCl. Double check that your units cancel, so we would be able to make 8 moles of HCl if, our hydrogen was limiting. If we'll do the same thing again for chlorine, we'll start with our 2 moles of chlorine, and then for every 1 mole of Cl2, we can make 2 moles of HCl. So, there we go. So we'll cancel out our moles of Cl2, and so if chlorine was limiting, then we would make 4 moles of HCl. So again, we would do two different train tracks, one starting with the hydrogen, one starting with the chlorine, both figuring out moles of HCl. And then we are going to look and figure out which one produces less. So this one produces less, the one from chlorine. So that means that chlorine is our limiting reagent because it produces less product. The chlorine will get used up first. There will be extra hydrogen left over. So chlorine is our limiting reagent. It produces less HCl, and this would be our theoretical yield. Okay, because we can't make 8 moles of HCl because we will run out of chlorine before we can. Chlorine can only make 4 moles of HCl, whereas our hydrogen could make 8. Okay, let's do another one. So this says, calculate the mass of water produced when 8 grams of H2 and 24 grams of O2 react. So again, we have two different reactants, right? We have a mass of hydrogen and a mass of oxygen, and it's asking to calculate the mass of water. So whenever you have both reactants and you're being asked to calculate how much product you can make, that is a limiting reagent problem. So anytime we're doing that, we are going to do two different train tracks, one to deal with the hydrogen and one to deal with the oxygen. So here we go. So if we had H2, we'll take it all the way through. We have our 8 grams of hydrogen. We're going to change our grams of hydrogen into moles of hydrogen using the molar mass. And then once we get moles of hydrogen, we can use our mole ratio to go from moles of hydrogen to moles of water. So for every 2 moles of H2, we will get 2 moles of H2O. And then once we're in moles of water, we can use the molar mass of water to change to grams of water. And then we can multiply the top, divide the bottom, and see how many grams of water can be formed. So here we have 71.5 grams of water if hydrogen was limiting. So now we will do the exact same thing for oxygen. Okay, so we'll start with our 24 grams of O2. We'll use the molar mass of oxygen to go from grams of oxygen to moles of oxygen. And then we'll use our mole ratio to turn moles of oxygen into moles of water. So again, for every 1 mole of O2, we are producing 2 moles of water. So then we can use our molar mass of water, right? For every 1 mole of water, right, we have 18.02 grams. Those cancel out. And we can multiply the top, divide the bottom to figure out how many grams of water can be formed. So now we have our grams of water for both. So we have 1 for if hydrogen was limiting, 1 for if oxygen was limiting. And we look and we see which one produces less. So we have less water here. So this would be our theoretical yield. 27 grams of water would be our theoretical yield because it is the one that is smaller. So that means that oxygen is our limiting reagent here because it produced less water. That means hydrogen is in excess because there will be extra left over. Okay, a couple terms. So theoretical yield is what we've been talking about, right? Like on this last slide, this was our theoretical yield. That is the maximum amount of water that could be formed based on the reactants that we were given. Okay, the actual yield would be like when you're doing the experiment in lab. You go and you do the experiment and you weigh it at the end. That would be your actual yield, how much you actually made when you did it. So the theoretical yield is always on paper, right, using stoichiometry, and then the actual yield will always be from lab or, however else you're getting it. And then the percent yield is a way of showing how well your reaction actually worked. We're always going to do our actual yield divided by our theoretical yield times 100. And this should come out to less than 100%. Because usually something, is spilled along the way, something happens. If your product was still wet at the end or contained impurities, maybe over 100%. Typically, though, it'll be less. Something usually gets spilled along the way in lab. So here is an example percent yield problem. Without proper ventilation and limited oxygen, the reaction of carbon and oxygen produces carbon monoxide. So our first step is to always write our balanced chemical equation. Carbon plus oxygen gives us carbon monoxide. So again, make sure you're following those Hofbrinkel rules to see which ones get subscripts and which don't. Carbon does not show up in Hofbrinkel, so it does not get a 2, but oxygen does, so it does get a 2. And then balance your chemical reaction. So this says, what is the percent yield if 40 grams of carbon monoxide are produced when 30 grams of O2 are used? So a lot of times people will ask me, well, how do I know the difference between this and a limiting reagent problem? Well, limiting reagent problems, you'll be given both of your reactants and be asked to figure out information about the product. Here, we're being given the product, right? This says it's the amount is actually being produced. This is an actual yield. And then we're being given a reactant. So we're being given a reactant and a product. Okay, so in that scenario, when you're given a reactant and a product, that is going to be a percent yield problem. This much was actually produced, and we're going to use this 30 grams of oxygen to figure out our theoretical yield. And then once we figure out our theoretical yield, we can do our actual over our theoretical to figure out our percent yield. So if you'd like to try this problem by yourself, here are your options, multiple choice, right? You're going to use your 30 grams of O2 to figure out your theoretical yield. And then that 40 grams of carbon monoxide is an actual yield because it's telling you 40 grams of carbon monoxide are produced. And then you can do that ratio to figure out your percent yield. So go ahead and pause here if you'd like to try it yourself, or you can just keep watching if you'd like to see the answer. Okay, so the first thing we're going to do is figure out the theoretical yield based on the amount of oxygen that we were given. So we have 30 grams of O2. We'll use our molar mass to change our grams of oxygen into moles of oxygen. And then once we've done that, we can use our mole ratio from the balanced chemical equation to go from moles of oxygen to moles of carbon monoxide. So for every 1 mole of carbon monoxide, we will get 1 mole of O2, we will get 2 moles of carbon monoxide. And then we can use the molar mass of carbon monoxide to go from moles of carbon monoxide to grams of carbon monoxide. And then we'll multiply the top, divide the bottom to figure out how many grams of carbon monoxide we get. Remember, pay attention to significant figures. So our theoretical yield is 52.5 grams of carbon monoxide. So if everything went perfect in this experiment, we would get 52.5 grams of carbon monoxide. However, things happen, right? And we didn't. We actually only got 40 grams of carbon monoxide, and that was given to us in the problem. So that 40 grams will go on the top the 52.5 grams of carbon monoxide will go on the bottom, and we multiply that by 100, and we will get 76.2% yield. Just so you know, this 100, this is always going to be exact. This is not determining our significant figures. That's just going to be based on measurements that we took. So there you go. Actual over theoretical times 100 will get you your percent yield. We do this calculation, and all of these actually, these theoretical yields and percent yields, we do these calculations a lot in lab because we need to know how much should we have made, how much did we actually made, how well did our reaction go, and is there something we could have done to make it go better, right? Do we have any sources of error? So that's going to be the end of this first lecture on Chapter 4. You need to practice these problems a lot. If you are not strong in stoichiometry already, I would recommend doing all of the lecture worksheet problems and maybe getting help on top of that. You can always come and talk to me in my office hours, or you can talk to our SI to get more help. But stoichiometry is a foundational part of chemistry. So if you're not strong in stoichiometry already, or if the stuff in this lecture was confusing, you need to really, really work on it because it will show up for the rest of the semester. This is a foundational skill, and you need to be really, really good at it. So get lots of practice, work on that Chapter 4 lecture worksheet, and I will talk to you guys next time.